Hi, welcome to the third video out of 4 videos for the cardiac system. So we're looking at blood pressure. We're going to look at what blood pressure is, how it's measured, what resistance is, some average readings, how exercise affects blood pressure, and then a little bit of revision at the end, blood redistribution, what is it and why is it useful to us during exercise. So let's start with blood pressure. What is it? It's a measure of the force of blood coming out of your left ventricle when the heart is contracting. So the heart contracts and this ventricle here contracts and forces all the blood out of the heart towards the body via the aorta, that great big artery. The blood rushing past and through that artery is what we call blood pressure. So we're measuring how fast, if you like, and the resistance against that blood in the vessel. So there are 2 measurements that we're looking at. We're looking at this systolic blood pressure, which is when this ventricle is contracting and the artery, the aorta, is full of blood. And we also look at diastolic blood pressure. So this is when the heart is actually in its filling phase, so it's relaxed and the blood is actually coming from the atria down to the ventricles. So these valves down here to the aorta are actually closed. So whatever blood is left in here is what was left in from the systolic part and is just travelling through to the body. So there's no more active blood actually coming through. The resting or the relaxed phase is called diastolic. So you would expect that that's going to be a lot lower in pressure than the pressure that's measured when the heart is contracting during its systolic phase, yeah? So this number here represents the systolic measure and this number here represents the diastolic. So the yellow number, the 120, represents the pressure in the aorta when the ventricle is contracting, and the 80 represents the pressure in the aorta when the heart is filling, when it's relaxed, when it's in its diastolic phase. Both of these, regardless of which one, is measured in millimetres of mercury, which is represented as mmHg. Millimetres being mm and Hg being the sign for mercury. So let's think back to the last video when we looked at Q. Can you remember what Q was? That's right, stood for cardiac output. So can you remember what the equation was? And can you remember what elements you needed to calculate Q? Just pause the video while you have a think about it and write something down. So the equation was Q, which means cardiac output, is equal to heart rate times stroke volume. Heart rate being the number of times the heart beats per minute, and stroke volume being the number of millilitres that can be held within that left ventricle. So the amount of blood forced out of the heart in just one beat. So there's your answer, much more neatly than I've just done it. So we have heart rate times stroke volume equals cardiac output. So why are we introducing cardiac output again? Well, cardiac output, the amount of blood coming out of the heart in 1 minute, determines the blood pressure, or helps determine the blood pressure. Because yes, we've got another equation to learn. Blood pressure is Q times R. When Q is cardiac output times resistance. So this is a new term for us. So blood pressure is cardiac output, the amount of blood coming out of the heart in 1 minute, times or multiplied by the resistance that blood vessel that it's travelling into pushes back onto that blood. So let's talk about that for a little. Right, resistance refers to the resistance of the blood flow, like I just mentioned, and the causes of this resistance can be 2 things. First of all, it can be down to the size of the blood vessel. And that depends, doesn't it, whether the blood vessel is dilated or whether it's constricted. So let's have a think about what those mean again. So if a blood vessel is dilated, and we're looking at this as a cross-sectional area, then we say the diameter is quite wide, it's been increased to allow for more blood to flow down. Vasoconstriction will be when the blood vessel is reduced in diameter. So the smooth muscle around the outside of that blood vessel has contracted to reduce that size. So why have I put a hose pipe? Let's have a think about that hose pipe and think, and I'm sure that you've done this with younger brothers and sisters maybe over lockdown, but you plug your hose in, you've got one water pressure coming out, okay? If you use the end of this gun here, you can change the way the water comes out. So if you took the gun off completely, the water would just flood out in front of you. So we'd say that's got quite low pressure. And the reason that that would have low pressure is because actually it's quite a dilated shape. It's quite a large shape for the water pressure that we have. If we reduce that size to a smaller amount, so we just pick some of these areas in the gun, so let's say we go for jet, which uses that gold bit in the middle, we're reducing the size, but the pressure, so that the cardiac output of water, the amount of water coming out of that tap hasn't changed, but we've increased the resistance because we've reduced the size of the hole. That means now the water is going to come out at a higher force, so it's going to go further, isn't it? And that's all we're doing here in the body with the arteries. We're dilating them and constricting them depending on what our cardiac output is. So let's talk about the thickness of the blood, because this is the other cause of resistance that the blood flow might come up against. People always say to you when you're exercising, stay hydrated. Stay hydrated is really important, and it is really important for so many things, like being able to think clearly for one. But if you are dehydrated, your blood becomes dehydrated. If you take some of the water content out of your blood, it's going to increase in viscosity, so it's going to get thicker. It's going to be like thick old gravy, as opposed to water. So a lower viscosity, a thin liquid. So the thickness of the blood can also cause a high resistance. So blood pressure increases when there is more resistance. So blood pressure will increase if the viscosity of the blood is high, if the vessels are constricted. If cardiac output increases as well, this will also increase blood pressure. Okay, so cardiac output increases the blood flow, so we've got more blood flowing out of the heart. It increases the speed of the heart, as we talked about with the hose, and therefore the overall force through the vessel is going to be higher. So hopefully that is resistant. So this is how the body will now record information about your blood pressure and make changes in the body if it needs to. So a very high blood pressure is dangerous, and I'm sure you've heard about people talking about, oh, I've got high blood pressure, or various things like that, and it's quite a dangerous thing. But we're not talking about that dangerous aspect of it today, although we might touch on it briefly later just because it's really interesting. But how does the body read that there is an increase in pressure? So we know from previous videos that receptors in the arteries can read carbon dioxide content, oxygen content, pH of the blood. And by reading that, it relays messages to the medulla oblongata to say, hang on a minute, we've got more carbon dioxide than we need in here, we must be moving. So can we increase heart rate and breathing rate, please, to try and get that carbon dioxide rate down? Really clever. The baroreceptors work in exactly the same way. They're specialist cells on the artery walls, on the inside of the artery walls, that are attached through the nervous system to the medulla oblongata, which can then work with heart rate, work with breathing rate, or we will now call the cardiac control centre and the respiratory control centre. So the baroreceptors will feed information to those two centres as well. It does this with a nervous or electrical impulse, and it relays messages from these receptors, from these baroreceptors in the arteries. And they are specifically to detect blood pressure. So they won't look at the pH of the blood, they purely look at pressure, all right, and the flow of the blood past those receptors. So what will happen then? What will the body do? So the body can detect if the blood pressure is too high. That means your blood's flying through at 100 miles an hour, bit of exaggeration, but it will dilate the vessels for you, so your blood pressure will be reduced. If the blood pressure is too low, then the vessels will be constricted to try and increase the pressure. So it just tries to find that homeostatic state, that state where it feels relaxed and happy. So let's look at changes in blood pressure then when we're exercising. Excuse me. So we've got two different types of exercise that we need to look at for our specification. We need to look at aerobic exercise and we need to look at resistance training. So average numbers for somebody doing an aerobic activity such as jogging would be higher than your resting rate, which was 120 over 80. We're now looking at 160 to 200 for your systolic, and for your diastolic, which was 80, stays around the same. We're going to explain that later on. If you are resistance training, the systolic pressure can go over 200 millimetres of mercury, and the diastolic in the case of resistance training also increases. So I wanted to talk to you about the section here that I've put on and this poster that I got from Anatomy Stuff, which is really good. And this is just because it's interesting, so by all means fast forward over this bit. These are long-term changes, these are issues that can happen with your arteries that are not in our specification, all right? But I just thought you might be interested to know. It's a common question. So up on the top here, we've got a lovely artery where nothing's wrong with it. It's representing here, and you've got all this gorgeous smooth muscle around the outside that will dilate or constrict depending on what the body needs. No problems at all. If we go up to this end of the scale, we've got issues, and this is what we call plaque that's built up on the side. And this is built up from all sorts of things, but cholesterol you would have heard of, and fatty deposits you would have heard of, and it can start to build if you have an unhealthy lifestyle. It builds under the inside layer, so it's not actually inside that artery as you might think, but it builds underneath. But this is a problem in itself. So sometimes, as you can see, when you get too much of this plaque, it causes a lesion, it causes like a bad spot, a weak area, and that weak area can break open and bleed. So what happens is you've got this slightly broken area in the epithelial layer, so in this cell layer on the top, and as the blood goes past, blood can tell, it knows there's a tear in this layer. So the blood will clot it for you because it thinks danger, obviously. That's how we get scabs and things like that. So the blood will try to clot it. You end up with a blood clot, which is also called a thrombosis. And this is now causing extra resistance to blood flow. We had some before, and now we've got extra resistance to blood flow. If it's really bad, it can block the artery completely, and obviously this is not good news. Can cause heart attacks if it's on the coronary artery, the one leading to the heart and things like that. So I just added that for fun, really, because I thought it was. So let's get back on specification, and we'll look at the changes in blood pressure to resistance training. So resistance training is anything involving a weight, so weight lifting. It can be body weight exercises as well, but bear in mind, the higher the resistance, the higher the pressure will probably go. So this is what I mean by this point. It's directly proportionate to the demand of the exercise. If the weight is light, then blood pressure will not rise to the same extent as if the weight was very heavy. And just to recap, systolic, so when the heart is contracting, blood pressure can go up to 200, and diastolic will go in excess of 85. Apologies, it will go in excess of 200, not up to 200. So, concentric contraction of muscles. Now, this is a new term to you, I think, but it means or refers to when these muscles look bigger in size as they contract. So the muscle shortens and gets fatter. That concentric contraction squeezes all the vessels that are within that muscle. So as the muscle gets bigger, it squeezes the blood vessels there. The heart responds by beating with more force because obviously the blood is now getting trapped, and this helps the blood pass through the vessels. So this is why if you've lifted a heavy weight, you might feel your heart start to beat quite hard. Now here's something to try. This is called the Valsalva method, and it's a way of lifting extremely heavy weights. So it is a technique. I felt quite sick when I found this out, but it is a technique initially to clear pus from your ears, the person who discovered it. But now it's used in weight training to lift really heavy weights. So give this a try. You take a deep breath in, you put your hands in front of you and you link your fingers together and you try and pull them apart. And you try to breathe out, but don't let any air escape from your nose or your mouth. It will cause a significant increase in the resistance around your thoracic cavity. This is your thoracic cavity, this breathing area around here where your lungs are. So your lungs will stay inflated, and as all your muscles are contracting around it, we're going to cause more pressure on those blood vessels all around the thoracic cavity, which can greatly increase the blood pressure as well. So hopefully you've had a go at the Valsalva method. You've given it a go, you've found the result. Now when I did it, I felt a little bit faint afterwards. Could you write down why you think I might have felt that way? What was my body's response to me lifting a heavy weight and essentially holding my breath but trying to force my breath out? So the Valsalva method, why that had the effect it did to make me feel faint. Pause the video while you do this, please. So for those of you who have written down an answer, the reason I felt faint afterwards is because of the baroreceptors, that would be a key word you'd need to say, have detected a distinct rise in blood pressure, both systolic and diastolic, more points given there. My body, in response to an extremely high and potentially dangerous blood pressure, is to dilate the vessels, which meant when I relaxed, my vessels had already dilated, so my blood goes through without any resistance at all, and it can make you feel a little bit lightheaded. So changes in blood pressure for aerobic, they're not that different. They do go up. Systolic rises between 160 to 200 millimetres of mercury, depending on your fitness. It can go higher than that. It used to be 120. So there's a raise in systolic pressure. There's a rise in the pressure when your heart is contracting, which you would expect. You can feel that when you're running. So that's self-explanatory, I think. The diastolic remains roughly the same at 80, which if you think about it makes sense as well, because there's no blood coming out at that part. It's the resting phase for the heart. But you've also haven't got large muscle contraction, so you've got no extra resistance on that blood flow or on the muscle, on the vessels. So the diastolic remains roughly the same 80. We have the exercise increases the heart rate. This increases cardiac output, but there is no change to resistance. So we know the heartbeat is beating faster and therefore venous return has increased, so therefore we've got bigger stroke volume and bigger heart rate. If that sounded like a foreign language, listen to the video before again, please. There's no change in resistance because we've got no large concentric muscle contractions, but the impact is that your systolic blood pressure increases. So the higher intensity, the higher the systolic blood pressure. So if you start sprinting and increase the intensity, your blood pressure will increase in sort of a linear fashion. So after exercise, what happens in aerobic exercise? You get a steady reduction in your systolic blood pressure. Now, everyone always says for you to do a cool down. Cool downs are really important. This is why. I mean, they are important for recovery and delivering that excess oxygen and taking away that excess carbon dioxide. But in terms of your blood pressure, it could cause you to faint if you suddenly stop. The reason for this is the skeletal muscle pump. So the skeletal muscle pump works in the same way as the concentric contractions did for the resistance training, but these are not big isometric contractions. So the muscle gets bigger and it pushes on the veins of your legs when you're walking or when you're running, and then when you release that contraction, you release the blood vessel, but then you move again and contract it. So it's a regular contraction, and the effect that has is to push the blood up the vein, so it increases venous return. Let me show you in a horrendous picture, I suspect. So here is your vein, and the anatomy inside there is that you've got pocket valves inside. Now the blood has to come up through here, and because it's low pressure, because it's returning back up the body, these valves shut the door and stop back flow of blood. Then the muscles round the outside contract and squeeze that vessel, which pushes the blood further up the body. Now if you imagine that this is being squeezed every time you make a step, so you step and this is your calf muscle, let's say, muscle contracts, relaxes, contracts, relaxes, contracts, relaxes. This vessel is squeezed in and out and in and out, so it keeps that blood flow going upwards. So to finish off the video, we're looking at redistribution of blood. Now we have done this before in section A2 of the muscles, but there are some new bits that we've added on. So first of all, let's revise that the average cardiac output, so that's the blood coming out of the heart in 1 minute, is 5 litres. That was half a bucket full. Vessel names that the blood travels through and in the right order were arteries, arterioles, capillaries, venules and veins. And if you remember, they went in size order as well. So these were the biggest and muscliest. These were the thinnest, only 1 cell thick. And these are quite thick and large, but don't really have much muscle to them. The arterioles link the arteries and the capillaries, and the venules link the capillaries and the veins. There, in numbers, are huge numbers, millions of capillaries, not as many arteries, not as many veins, more arterioles than arteries, but not as many as capillaries, and venules, less than the capillaries and more than the veins. Now, we looked or discussed that not all vessels are used. So some vessels are there, we can use them, but we choose not to use them. I think in lesson I would have spoken to you about roads, and that you've got a lot of people going down the motorway, but not all of the A roads are used, certainly not all of the B roads. And it's that principle really, that the body will move the blood where it needs to go. So the blood will move from inactive organs and muscles and shift that blood, shunt that blood to active organs and muscles. So as an example, if you have working muscles, if your muscles begin to work, so you start running or you start lifting weights, it will increase blood flow to those specific muscles. At the same time, it will then reduce blood flow to the digestive system, because now it's not as essential. We have the blood around the digestive system, we need it at the working muscles, it's more urgent, so it will take it from the digestive system to the working muscles. We'll increase blood flow to the skin. Now this is a whole nother section that we do at the very end. But this is about cooling and temperature control. So you'll get red-faced when you start to exercise and you'll sweat. And this is because blood has been redistributed to the capillaries underneath the skin to allow evaporation, to allow that heat to escape. So vasodilation is when the smooth muscle increases the diameter of the vessel. Vasoconstriction is when the smooth muscle contracts the vessel and reduces the diameter. This redistribution can also be referred to as vascular shunting, and its purpose is to redistribute the blood for oxygen delivery, for food delivery essentially, and to get rid of waste products, and also used for controlling body temperature.